window. Okay, I'm ready.
Okay, should we go ahead? Okay, welcome to the Earth to Earth seminar. Thank you for joining us today on the 25th of March 2021. As a reminder, the mission of Earth to Earth is to engage the UK geoscience community with inspiring science from internationally leading researchers to promote inclusivity and diversity, to support early career researchers and highlight geoscientists' contribution to addressing global environmental challenges. It's open to all UK institutions to participate. For questions, please use the Q&A channel on the bottom of your Zoom window. These may be posted at any time during the seminar, and we'll have 10 minutes at the end for me to relay your questions to the speakers. So now it's my great pleasure to introduce today's speaker. We're fortunate enough to be joined by Professor Dabo Guan. Dabo is a joint professor in climate change economics between Tsinghua University and University College London, and he's a fellow of the Academy of Social Sciences in the UK. His research specialises in environmental economics for international climate change mitigation and adaptation, and he was a lead author for the IPCC Fifth Assessment Report, AR5. He was a highly cited researcher in 2018 to 2020, and his paper about climate change impacts on beer consumption received the 2018 Altmetric Top 100 Award. Today, Dabo will be telling us about global climate change mitigation under the COVID-19 new normal. So thank you for joining us today, and please take it away.
Thank you, Simon, and thank you for the invitation and the introduction. I'm gonna share with you some recent work we have done on the global climate change mitigation, and together with some COVID economics, what we have been doing over the last year or so. So before I really jump into the topic, I'd like to introduce you our data set, which is publicly free and freely accessible, and you can find lots of data sets we developed and share to the academic community. It's called the China's Emission Account and Dataset. So it provides the up-to-date energy, emission, and socio-economic accounts for China. And the recent couple of years, we're starting to add our work on completion of the emission inventories for developing countries. Some developing countries where you don't usually have the statistics access to. For example, some African countries, Ethiopia, Uganda, some South Asian countries like Myanmar, Laos, etc. And you would be able to find some regional emission inventories for those countries, for large countries like China, the provinces, city level, and also the Indians on the states level, and the Russian on the federal states level as well. So we, myself grew up with this climate change mitigation research about lots to do with the data. So I was handling a lot of data when I was basically starting my academic career. So when they started, I compared the different data sets. I always find there are differences. Sometimes big, sometimes small. So there's always differences between the different data sets, although they talk about the same country or even the same sector. So it is really triggered me a lot. And then I trying to dig the information on the methodology behind that, but I rarely find that any data like publishers or like data agencies, they would fully and transparently tell you how do they actually account their emissions. So a number of years back, we started this SEES data set. So our aim is trying to fully, transparently provide all the data and freely to the academic community. So we first start with the Chinese emissions and historical emissions, and then later on they dive into the provincial or the city level. As I said, then in recent couple of years, we're starting to compile the data for developing countries. All the emission data, they are all, by using same, recommended by the IPCC, the statistical standard, and then all the data is in the same format. So it doesn't matter it's a national data, it doesn't matter it's China or it's India, is what we publish on the website is always have a 47 social economic sectors and by 20 different energy types. So it's a city level and then provincial level or state level is all the same. And so therefore you can make some comparisons, and then you can make some verification, cross-checking and verifications on that. The data sets has, firstly, on the national level on China, that has from 1997 to 2018 right now. So we recently updated the 2018, and for the energy and the emission inventories. And what can you use those data for? So it just give you a very a short a summary. What can you use that data for? So a couple of years back, we published a paper in Nature Geoscience, really to use the data to really to see when the China's emission peak would be and how the emission would peak, what's the level of emission peak, and what's the driving forces behind that. So I'm not gonna go into the detail a lot, but just basic saying in terms of our estimation, emission estimation, we find China is actually reach some sort of a high peak level in 2013, and then follow a slight emission like a decline in the number of following years. Although in recent years, like since 2018 and 2019, they grew up a little bit, but it's still fluctuation along the 9.5 to 10 gigaton level. And such emission kind of peak, suddenly peak, is if you look at the first figure, it's basically the China's emission is going up really quickly until 2010, 2012, and then starting to smoothing their emission trends since 2013. This is due to the one part is due to the energy mix, and China is starting to use less coal, so coal consumption is go down. But it doesn't necessarily mean that the Chinese energy consumption is actually go down. It's actually going up steadily, but the gap because of the coal reduction is fulfilled by the natural gas and renewable energies. And the data sets also include the 30 province regional data for China, like emission data for the 30 provinces. And then, that you can do lots of other type of things. One of the most straightforward, you're trying to see the per capita emissions, is actually the per capita emissions in, traditionally speaking, the more advanced regions, their per capita emission will be higher. Like in Shenzhen, Shanghai, Beijing, they are similar like that. But in China, slightly unique thing is that in some poor regions, like a relatively lag behind regions like Inner Mongolia and Ningxia in the west part, their per capita emissions is even higher because they produce lots of, they have a lot of comparative advantage on energy, the factor endowment on the energy, and they dig the coal out and sell it on. And if not, then they use the coal to burn the electricity, to generate electricity, then sell it on further. And if not, then use the electricity to process aluminiums or other metals. So those regions are really high emission intensive regions because of the endowed with lots of coal there. The data, as I said, the provincial level, national level, also we dive into the city level. This is a 300, roughly about 340 cities in China, and you can see lots of blanks there. This is what we haven't been able to compile the emission because of either the lack of data, like primary data, or there's just no enough time and there's labor to do that. But nevertheless, over the from 2005, and then we actually updated 2018. So you should be able to find on the data sets. Depending on different years, you should be able to find full emission accounts for 100 cities to 300 cities, depending on which kind of years we are talking about. These all those emission data so we compiled is really, it's through this emission inventory development, but we need to to verify it before we can really say the data is robust or is accuracy. There's a number of different ways, and lots of people are starting to use satellites or you use some monitoring data to do that. A part of my research group is trying to do that as well. But one other thing so we're trying to see, especially when we develop our the data, not only within China, but also beyond China to the more other developing countries. Those developing countries like a foundation of the statistic systems is not so advanced, let's say, and it's not complete. And it's quite important to verify their data before we can really use it. One of the ways we are trying to do is trying to identify the key pollution sources. So we're trying to establish the emission database for key pollution sources. This is like the key infrastructures. We have done a number of that. This is a couple of cases here. The first one is a global refinery emission sources, like the refinery oil and natural gas, basically refinery plants. And so globally there's a 1,400 plus plants, and we verify this their emissions. We collected the basic informations plants by plants, and calculate their emissions, verified with some other sources, and trying to really to get this like plant level of the emissions. Because when you have especially when you do a city or small countries, you may only have a few key pollution sources. If you have those super kind of polluters are fixed or verified, then you should be able to get pretty much the magnitude of the emission right, and then you can really focus on other sectors later on. So on the left-hand side, the refinery, on the right-hand side is a steel works. So it's basically steel and iron processing and productions. And globally, there's almost 5,000 plants and over 20,000 of units of the data to be processed. And those work, the steel work is actually undergoing right now, and we are still trying to compile the data more complete way and analyze it in a more academic way. The one of my research group led by Professor Zhu Liu, also in Tsinghua, during the COVID last year, basically during the lockdown period, we set up this carbon monitor kind of like a platform, trying to provide not really a real time, but a near real time. We roughly have a roughly 1 month lead time, like a time lag time, because we have to process this emission is almost real time monitoring is based on the real-time electricity data globally, available for roughly about 45 countries. And then some countries, some it can be up to about 80 countries, depending on the accuracy or under the spatial resolution of the electricity we really want, the electricity sector we want. Also, we compare, we as I said, we have this plant level data, we combine them and starting to use the carbon, the satellite images data to verify this in a more coherent way. But overall, so this we provide this on the website. If you interested in carbonmonitor.org, and you could look at the by country level of the comparisons of the emissions, and by different continents and by the countries as well. You have Europe, you have US, China, India, including roughly about 45 countries individually. And if we group by the regions, it's up to 80 countries in the regions. Okay, those are the basically the data we actually developed, and we actually all those data are freely available as C's website. And if you're interested, you could go on the website, can register and then download it. Everything is in the Excel sheet, so Excel file. So it's pretty straightforward. We have this the data, and then we want to use that to make some analysis. And because of the COVID, myself, I'm a climate change economist. A lot of the, I only show the one part of the data is the emission data, because we talk about global climate change today. But on the other hand, we have the global trade data or the global economic data, trying to look at how the economies is being affected by the COVID. So really is here. I want to talk about the COVID impact on the economy. There has been a lot of report since the second half of the last year, but we actually started to make some projections for the cost of the economy because of the COVID. Last year in March, so when the COVID first started, in the the European countries starting to establish the lockdown measures. And also we want to answer some key questions that in terms of the emissions, CO2 emissions, and then because the COVID will give some like a decline of the emissions because of all the economic activities been limited. And then this is temporary, or this is gonna lead to some long-term structure change. Whether we are gonna bounce right back. So this is the key things we want to answer. So before we really can answer that, there's two parts we need to do. Firstly, we really need to see what's the impact to the economy because of the COVID. As I said, in the March last year, we start to configure this as a study, and we develop a number of scenarios to look at how this the COVID would impact the global economy, including every country in the world. And we had and then because of China versus US and then EU, and they have a different attitude at the beginning, a different attitude to for this lockdown measures. China is very strict. So China will shut the the country, and then everybody will stay at home and have a very strict policy, and roughly lock down the whole country roughly about for 2 months. Then their cases reduced to around to zero, and then they start to ease off, step by step. But comparatively speaking, in the Europe and the US, we were in March last year, we started to say, okay, we should do some herd immunity things, and this is a big a code basically. It doesn't really matter. So we really have not very strict measures to keep people indoor, and then we have a longer period of lockdown. And also we actually suffered several waves so far of the COVID. And we're trying to compare. At that time, we didn't know there was a future waves or whatsoever. But we're trying to look at what will be the economic response for that. And this is going to be quite complicated to explain for so many graphs here, but we just look at the two graphs on the top left, and the bottom right on the I, basically the red color pictures. The first one is basically the China only, the one China first day lockdown. The assumption here, if every country in the world at that time, in January, that time in last year, would follow or will be in line with the Chinese lockdown policies, or like say the containment measures, to have a very strict lockdown policy for a very limited small amount of time, as the shortest duration, let's say 2 months, the global economy will only suffer roughly about 3.5%. And then the majority of the loss will be in China, where they initiated the lockdown. There will be some indirect consequences for other countries in the Europe and the US, including other countries, but they will be minimal because there's no direct lockdown. But at that time, if UK and then Europe and the US would have some more strict kind of the travel policies or whatsoever, and then the world economy losses won't be that high. But because we didn't have that, and everybody was doing, every country was doing what they are, and then we really end up into a not very strict of the sort of lockdown, and for pretty much a longer period of time, and the costs will be higher. It's about 30%. So basically, the first insight from this result really saying is that the strictness is not that important in terms of the global economic consequences. Duration is much more play a much more stronger part in terms of determining the global losses. Because every country in the global supply chain, one country implements the lockdown, or then the other country would indirectly suffered. And this one would basically showing the comparisons between, like the first one is when China first lockdown, and Vietnam didn't have, but Vietnam has a very close trade relationship with China. Therefore, their indirect loss along the supply chain is comparatively larger than the countries like in United States, for example, or New Zealand, where it has a less trade less trade dependency on Chinese exports. But when the US and then the UK started, like Europe is starting to make a more implement the containment measures, they're trading the close trading partner like Nigeria, Jamaica, for example, and they would suffer a lot indirectly, because if we take Jamaica as an example, they are pretty much rely on the US and European countries, tourists and other like services-based activities. So once this has been limited by the US and Europe, and the indirect loss for Jamaica is very high. And another thing is both Kazakhstan and Jamaica, Mongolia, they're very much a single dominating sector. And one sector, their economy, one sector is pretty much fall, then the whole economy is at the blink of the, so basically the second insight for this analysis is really trying to show the importance of propagation effects through the global supply chain. Some countries may not directly affected by the by the virus or whatsoever, and then indirectly they will. And the most important, the low and the medium income country would be more vulnerable in terms of the supply chain shocks. We also compare the sectorial level and to look at the the production sectors. And in particularly, we had examples about the comparison between German car industries and the Chinese electronic industries, because both sectors are global sectors, and it doesn't matter BMW or Mercedes, they all, their supply chain stretch to the globally every corner of the globe, pretty much. But compared with the Chinese electronic sectors, their supply chain is very much sort of comparatively regionalized, because China itself, they would provide lots of the supply chains, and the surrounding China, like Japan, Korea, and like even Vietnam, etc., they would provide other parts for the electronics. Another thing is electronic sectors, they are very much they can be substituted. Substitution effects is quite strong. But compared to the German car making industries, if you have some, they are very much rely on one or two specialized suppliers in some of their parts. So when they're doing the recovery, comparatively speaking, the electronic sectors in China is much quicker, much more resilient than the German car making sectors. And then we actually look at the future kind of waves. What would be the future waves, and how would damage further to the global economy? So we did 3 scenarios only. Basically, firstly is like when they firstly locked down, and everybody experienced the first lockdown, and then the easing off the economy step by step with caution, rather than just suddenly lifting it out. This is what we call, if you do that, then the global economy losses together will be roughly about 40% cumulatively, all together. And then if you don't do that, then you suddenly, like what we have actually done, when this is become a better, then you just quickly lift it up. Then the next waves comes in, and you start. There's 2 options. One option is you do the very strict policy, but limited the duration into a very small amount of, like I say, 2 months, and a very small amount of lockdown, versus like you have a longer term lockdown, but not so strict policy. Comparatively speaking, the short and the stricter and the shorter is much better in terms of the economic consequences. So this is the economics. There's this I only showed a few like illustration about the scenarios we done, but we actually had 48 different scenarios under this. So each of different combination of the scenario, it reflects how they are gonna go further in terms of the global economy would do in the next in short term, and possibly long term as well. And this would have big consequences for how this climate change targets, and how would the climate change mitigation would go after this COVID, beyond this COVID period. So back in April last year, and then the Climate Action Tracker, quite a famous climate kind of NGO kind of consultancy company, basically, was issuing like report, a hypothesis, basically saying how would the economy would go after this COVID. Every time they have a big disaster, so there will be a stimuli kind of a package available for pretty much every country. Where those stimulus go is going to go for the green sectors, or there's going to go for green sectors. Then we want to model that. Basically, this is just from their report. It's like a demonstration where they go. Lots of discussions is about, okay, there's a possibility the last chance for the global climate change would achieve something meaningful. And we are actually trying to quantify that and see whether we are gonna go for a long-term structure change towards green recovery, or we're gonna bounce right back. Firstly, we select 80, roughly 7 times major economy in the world only, which account about 80% of global GDP and 90% of global emissions. But this doesn't include those low-income countries, which I will discuss later. Compared to these, the initial response for those countries, every country suffer the COVID. We want to go back to where we were before. So we actually want to go back to where we were before. It doesn't matter how many waves. We had like a number of waves, up to 8 waves in the next couple of years, and then the strictness, and then we all want to go back to where we were. But the real case is happens, the stimuli, when the stimuli comes into that would actually will impact current and even most important, the future emission patterns in the world. And, again, we did many scenarios, but I want to talk 2 things. One is that the right, on the left figure, the right curve basically tells you if all the current stimuli, we collect roughly about 40 countries stimuli plan from their government report. If we're assuming that if all the stimuli is go on to the high-tech industry sectors, and then basically like say 5G or the green infrastructures, like wind, solar, the green industries and the low carbon technologies, if many investments are going in there, the emissions will go back a little bit, but will possibly in line with the 2-degree C targets, and we still have a hope for achieving, like say, do the climate change mitigations. But many countries, including the previous Trump administrations, and some developing countries saying, okay, we wanted to have, over the next 5 years, we're gonna invest 1 year's 10% GDP over 5 years time period on like infrastructure sectors. But if we assume those infrastructure means coal power plants or like cements or all those things, actually we're gonna basically say we are gonna say goodbye to the global climate change. We are gonna go say, okay, yeah, we are never going back to the 2-degree C target, because if you invest those into the plants, cement plants or the coal power plants, you're gonna lock into that cycle, because in the next maybe 30 to 70 years, you're gonna keep burning coal, keep producing cement, etc. So this is basically on this. This is very important if we really want to achieve the global climate change mitigations. We need to keep the goal on this green recovery, so green infrastructures and the green sectors, and this is very important. That was a major economy, like including US, China, Europe, India, etc. And let's take a look at some almost like a forgotten corner of the world. We selected roughly about 60 countries. They are not usually in the center of the world, but they all have one common character. Over the last roughly 10 years, from 2010 to 2018, over the 8 years time period, those 60 countries are actually growing. Their emissions, annual emissions, is actually above the world average. And there's actually 62 countries above the world average. The other 2 are India and China, because they are too big compared to those countries, and we remove them. We only want to talk about those, let's say, relatively small countries. And those countries, per capita emissions or emission growth rates are higher than the world average over the last 10 years. And for some of the countries, they are even much, much higher. And for example, Myanmar, Zambia, Laos, if you look at the left corner of the left panel, the left figure, the left panel, so the vertical panel, Laos, their emission grow over the last 8 years, grow over 6 times. And their GDP growth is roughly about 70%. And Myanmar, also another South Asian country, their emission grows 3 times. Their GDP grows roughly about 60%. So this really is about every unit of Myanmar's GDP kind of additional GDP gain, they would consume 3 additional CO2 emissions, basically. Of course, Myanmar right now is in some political crisis. We don't know whether they are going to go, end it very soon, but this is what the historical data shows. So once they stabilize their economy or political settings, and then they try to be getting develop, and then this become really emissions is contribute more. And among these 60 countries, none of them are significant, individually significant to the global emissions, but together, 60 countries together, they rank at the 3rd largest emitter in the world. The first is China, and the US. It's pretty much similar to US. It's about 60% more than the real 3rd largest emitter, like India does. So it's and the most important, they are growing really fast. So we were actually really trying to zoom in. Firstly, is establish kind of develop the emission accounts for them, and trying to establish some long-term trajectory for them. Firstly, let's take a few. I won't be able to show all the 60 countries, but a couple of examples. Myanmar, I like to use the example here. On the left corner, the top corner, it shows you the annual GDP growth is 7% over the last 8 years. Emission is 19% annually. So let's say that every 1 unit of GDP they additionally they roughly require 3 units of additional CO2 emissions to support that. And what's the driving force behind that? From 2010 to 2018, Myanmar's emissions grow from 7.7 to 30.2. So it's driven largely by GDP per capita and oil and the energy intensity. This is the reason because in 2011, Myanmar's political, things become stabilized. They actually open to the investment. Lots of oil imports. They actually privatized their oil sectors. Lots of small petrol stations and then oil kind of related industries. And they're starting to develop the manufacturing, real estate, and starting to build houses and infrastructure, etc. They used to use a lot of biomass. Because they were poor. As soon as they got a little bit richer, they quickly switched to commercial fuels, like say oil, and power generation by using oil, etc. So the energy structure become a much more fossil fuel based, and this is the trigger to their emission growth so quickly in the recent years. Of course, they're starting to do lots of trade with China, with other countries as well. So this, we can skip that for now because of the timing issue. Ethiopia, we want to make some comparison with the Ethiopia. Ethiopia, the GDP growth is about 10% per year, and emission is about 11% per year. So it's in parallel. It's not so bad compared to Myanmar, but it's still quite significant. The growth is quite quick. One of the difference compared to the Myanmar's growth rate is that population growth accounts for quite a significant big chunk for the Ethiopia's emissions. The population from 2010 grew from 88 million to 106 million, roughly about 3% per year. So it's quite significant in terms of in terms of the compared to other countries. Ethiopia is also become more industrialized. They have a more manufacturing sectors, and especially their service sectors is very, very interesting, because they trade or they buy a lot of aircraft from Europe, from US, and possibly you guys, some of you may know that Addis Ababa, the airport, they become a major terminal for Africa countries, and they actually buy those flights, aircraft, and to carry the services to make the aviation services for other African countries. So this is a very interesting phenomena for Ethiopia. So we actually did for all the 60 countries, small countries. So when we talk about, and we want to know what will be the future like. And then there was a past from 2010 to 2018, and we want to know what would be the future like. So we set up a few scenarios here. So on the right-hand side, you will see a number of dashed lines. Those are actually our scenarios. You can just forget about SSP1, SSP5, which we use that as a boundary to see what will be the boundaries of the best emissions you could get and the worst you could get. And all our scenarios is in between. Firstly, the WPS is what we call a weak policy scenario. What does that mean? It basically means, we had COVID and 60 countries together. They will, between 2020 to 2024, and because of the severe, we project they will go back to their emission will go back to not pretty much to where they were before, but very closely, roughly 96% to where they were before, and then we grow from there to have no weak policies. There's no climate policy on that, and they just go along with their historical trends. And another thing is about historical trends. Many of the current integrated assessment model or the large model, their base year are in 2010. They couldn't capture the rapid change over the last 10 years happened to those small countries. So to this work, we actually have to update their SSP kind of trajectories for each individual countries, for the small countries there, and to make these projections and to make them to in line with the historical trend will there be. And then we have a two, not really realistic, but we call the low carbon technology and the extreme low carbon technology. What does that mean? The low carbon technology means that the orange color of the line is that we assume that after 2025, every newly increased vehicles, all newly increased vehicles from 2025 to 2040 will be electronic, but in a linear, gradual implementation way. And for the electricity sector, for the fossil fuel-based electricity sector, they will gradually, in a linear way, to all the newly added capacity of the electricity sector will have a carbon capture storage. As I said, it's not gonna we didn't plan to do the like a realistic scenario. This is we want to see what will be the best or the low carbon will be. Even with that, you're gonna see some very significant emission growth on that. And even with the green one, the extreme low carbon, that is even have a much stronger assumption that all newly added electricity power or will have a CCS feature right away. And all newly added vehicles in those countries will be electric right away. So this is even extreme, more extreme. Even with such a strong kind of assumptions, we can see significant emission growth. There's gonna be no, almost not say even see reduction, it's no slowdown almost. Well, they will slow down a little bit, will bend the curve a little bit, but it's significant growth for those small countries. So that's the trigger to ask this next question is that, what's the carbon space for those emerging emitters? We call them emerging emitters. What will be the carbon space for what emerging emitter would require? And then if you look at the left corner, this is, we calculate this pretty much they require. And yeah, by 2040. And then there's some space left for, if we still want to have a 1.5 degrees C target, there's some space on there. But that's left for rest of the world as a whole, including China, US, EU, India, and then many other countries there. If you look at it on the right-hand side, we compare the three scenarios we had: weak policy, low carbon, extreme low carbon ones, and against with the 2 degrees C and 1 degree C targets we have there. And then the x-axis is that annual emission change of the CO2 for those the emerging countries, and the y-axis is the rest of the world. China, Indian, US, and the EU. What do they need to do to compromise the emission space required by the emerging emitters? So basically, like say in the weak policy scenario, if we still want to do a 1.5 degrees C, is that those small countries will annual emission growth was roughly about 3% together, their increase. That if we still want to have 1.5 degrees C, the rest of the world, including the US, EU, India, and China, would together need to reduce emissions by 15% to accommodate the small countries' emission growth, as well as decarbonize their emissions to achieve the 1.5 degrees C from 2020 to 2040, basically. So really, so the conclusion is that it's not, well, those small countries, when they stabilize and then they require the development, they have a right to develop. But the important thing is how the rest of the world, including US, EU, including also China and India, could be able to help them to really to decelerate their emission growth, and then to trying to flatten their curve to have a less cumulative emission in the next few decades, and eventually to achieve the emission reductions overall for the entire countries. So I think I'm gonna stop here, and thank you very much for that. There's possibly quite lots of intake, but please, I can answer any questions you have raised. I hope I kept the time.
Yes, thank you, Dabo. That was yeah, perfectly kept the time. Thank you. That was fascinating. Thank you very much for that talk. Okay, it looks like we have some question here for you. I don't know if you can see that. It says, how do you check the accuracy of industrial CO2 emission data Is it self-reported or independently verified?
Yep. I will. Yeah. Okay. I think it complies with all the Chinese data and the emission. This is not collected. It's developed or compiled by ourselves. Not saying myself necessarily, but my research team. And we actually had a way to account to compile these emissions, what we call crowdsourcing, but not crowdsourcing money, but crowdsourcing data. So I didn't have the time to show the mechanism here today, but we actually publish all this data available. We develop ourselves and online freely, and then we also call for people who are interested to develop the data for their hometowns or for their own countries, and yeah, so this is on that, and then they can join us. And then on the some more like a daily basis, we have roughly about 50, 60 people working together on to do the data compilations, collections, etc. And then in terms of the uncertainty, sure. All those data we get on the city level, provincial level, and even the developing countries, you can find we trying to firstly to fill the blank there. So the first most important for the emission data is that from 0 to 1, so to none to available, and from availability to robustness or accuracy. There's several steps doing that. Once you have the data, then you need to be transparent, which in our data, we fully transparent. We tell you how we did, all the assumption we made, and then, this whole thing. But unfortunately, major data agencies like IEA, EDGAR, or in the US, CDAC, if you look at the methodology document, there's a basic black hole there. And there's not enough transparency about where their original data come from, what's their emission factors is, and what's the process they compile the emissions. I actually host a workshop 2017 to invite the key stakeholders from IEA, EDGAR, and CDAC, and to just talk about the methodology to open the black hole. Black box basically there, and then yeah, so but I think the second step is transparency, and then it's a comparability. So whether you can compare, like I said, I have a city level, and you add up whether it's equal to national level, and then all the nations add up is pretty much as the global level. So it's a comparability, and between also different data sets, comparability. And the fourth is the verification. The verification is including the inventory techniques we have, and with monitoring, or with other kind of like satellites, everything. Each of them have a large uncertainty themselves anyway, but it doesn't stop. We should work together to do the verification for that. After the verification, then you really can talk about accuracy or robustness. All the things we do on the Chinese city level, or the emission for the small country, for the emerging emitters, they are all pretty much very limited data available. We try to fill the blank here for now. So yeah, so this is that. The overall, there's another question is about the overall yeah, the global CO2 emission uncertainty. Well, people having different views on that. If we talk about the global CO2 emissions, we have to separate that with man-made, which is human-induced, which is fossil fuel, or natural kind of nature one that will be hugely
think we may have lost Dabo. Okay, we'll give him a couple of seconds to see if he can rejoin. Okay, in the meantime, I will mention that next week's, there will be the next seminar will be coming up in 2 weeks' time, I believe. And that is the small and mighty, the role of microbes and minerals in melting the Greenland ice sheet, which is by Dr. Stephanie Lutz from Geneva, and also by Professor Leanne Bennett will be taking that one. So it looks like, should we wrap up now, I think? It looks like we might have lost Dabo there. So it just remains for me to although he's absent at the minute, I'll thank Dabo for a very interesting talk on a very timely topic. And thank you to everyone who's attended this seminar and everyone for watching on YouTube. And we hope you can all join us again for the next seminar in 2 weeks' time. Thank you very much.